Hello, discrete math fans. We're going to talk about an amazing formula called Binet's formula. It's going to compute Fibonacci numbers for us. Now let's suppose you wanted to compute the 1000th Fibonacci number. So the notation we're using is f sub 1000. This is not actually a difficult problem. It's just tedious. We want to make sure that we're keeping a distinction between difficult and tedious. Difficult or hard is something where you have to do a lot of thinking, you have to work very hard at what you're doing. Tedious is where a problem is rather easy to do, but it takes you a long time to do it. You'd have to use the recurrence for the Fibonacci numbers, all the way until you use the 1000th Fibonacci number. Now it turns out, actually, there's a really nice formula. It's a closed form for the nth Fibonacci number. It's a formula where you can just plug in n and it'll just tell you what f sub n is, and you don't have to compute any of the previous numbers. If you're using the recursion, you need to know what is f sub 998, f sub 999, add them together to get f sub 1000. Now we can do it without computing those previous values. First, let's talk about some preliminaries. Let's take this quadratic equation, x squared minus x minus 1 equals 0. And let's just use the quadratic formula to find its real solutions. All right, so let's not go through all the details. If you use the quadratic formula, you get 1 plus or minus root 5 over 2. And as a matter of notation, let's call the positive root, 1 plus root 5 over 2, let's call that phi, and the negative root, 1 minus root 5 over 2, we'll call that tau. Now phi is a very well-known number in mathematics. It's known as the golden ratio. It shows up in lots of unexpected places, things you wouldn't expect the golden ratio to show up in. All right, now we're ready to state Binet's formula. So first I'm going to give you the formula, then we're going to prove a lemma, and then we're going to prove Binet's formula. So Binet's formula says that if f sub n is the nth Fibonacci number, then f sub n is phi to the n minus tau to the n all over phi minus tau. That's it, a really nice formula. Now before we go and prove Binet's formula, let me just show you how you could use it. All right, we know the Fibonacci number sequence starts f sub 1 equals 1, f sub 2 equals 1, f sub 3 equals 2, 3, 5, 8, f sub 7 equals 13. Now let's plug in n equals 7 into Binet's formula, see what we get. So f sub 7 is phi to the 7 minus tau to the 7 all over phi minus tau. We'll plug in phi and tau into this. One thing to notice is that this denominator, which is always just going to be phi minus tau, it's just square root of 5. All right, and the numerator will have phi to the 7th minus tau to the 7th. Not a whole lot we can do to simplify that. Now if you plug all that into your calculator, or some kind of symbolic calculator engine, you'll get 13. That is a miraculous formula. How is it possible that something with so many fractions and so many instances of square root of 5, how could that possibly produce a whole number? Furthermore, how could it possibly produce the correct Fibonacci number? It has no reference to previous Fibonacci numbers. All right, well, let's prove Binet's formula. All right, so before we get to the main proof of Binet's formula, we're going to prove a technical lemma that will help us out. So the lemma says that if x is any solution of the equation x squared minus x minus 1 equals 0, namely x can be either phi or tau, then for any n in the natural numbers, x sub n will be equal to x times f sub n plus f sub n minus 1. And I'm going to mark this equation star because we're going to write a proof for this, and it's actually going to be a proof by induction. All right, so here's the proof of the lemma. Later we're going to prove Binet's formula. So let P of n be the predicate marked star, and let x be any solution of x squared minus x minus 1 equals 0. You're keeping in mind that x can be either phi or it can be tau. All right? We know that f of 1 is equal to 1 and f of 0 is equal to 0. So x times f of 1 plus f of 0 is equal to x. So that tells us that P of 1 is true. All right, now we'll go on to the inductive step. Let's let n be a natural number, and we'll assume that P of n is true. That is, we're going to assume that x to the n is equal to x times fn plus fn minus 1. We want to show now that P of n plus 1 is true. That is, we want to show that x to the n plus 1 is equal to x times fn plus 1 plus fn. All right, let's mess around with x raised to the n plus 1. We can split that off as x times x to the n. And then that's all equal to x times x fn plus fn minus 1. That's our inductive hypothesis. Right? Our inductive hypothesis says that xn is equal to x times fn plus fn minus 1. Then we can just distribute the x. And now that x squared, this x squared here, turns into x plus 1. All right, why is that? Remember that x is any root of the equation x squared minus x minus 1 equals 0. So moving things around and solving for x squared, you can get that x squared is equal to x plus 1. We're just doing algebra here. That means I can replace x squared with x plus 1. Now we can do a little bit of algebraic manipulation. Imagine distributing the fn and then collecting the terms that have an x in them. And now fn plus fn minus 1 turns into fn plus 1. So this turns into this. All right, why is that the case? That's just the definition of the Fibonacci numbers. That's the recurrence. Now we've got what we want. Therefore, P of n plus 1 is true, so by the principle of mathematical induction, P of n is true for all n in the natural numbers. So we've proven this little technical lemma. Now we're going to prove Binet's formula. All right, so we're going to prove Binet's formula. Let's let n be a natural number, and according to our lemma, we can say that phi to the n is equal to phi times fn plus fn minus 1. And the same for tau. Tau to the n is equal to tau fn plus fn minus 1. Remember that the lemma applied to any solution of the equation x squared minus x minus 1 equals 0. And so here we're specifically allowing x to be either phi or tau. So if we subtract, we'll get phi to the n minus tau to the n is equal to phi minus tau times fn. And now, if we solve for fn, we get our final result, that fn is equal to phi to the n minus tau to the n all over phi minus tau. So that proves Binet's formula. So we had two steps there where we had to prove our lemma, and then Binet's formula's proof follows directly from the lemma. Okay, that's all for now.